will be starting around 10 o'clock. Two ways to communicate if you've got questions today: through the chat, or also you can communicate through the Q&A or questions and answers. The screen points out here where the Q&A button is at the bottom of your screen, and you'll be able to type in your questions and look at that for them. Today we're going to be mainly on fertility. Jason Clark is going to be our main speaker, and we will have the codes for the presentation at the end as far as CCA is concerned. And so again, when we hit the top of the hour, we'll get started here. See, we're going to that. So just want to introduce Jason Clark. And Jason has been with us here at SDSU now a couple of years, and he is our extension soil fertility specialist. He comes to us from Utah State, and he's working on getting updates to the nitrogen, phosphorus, and potassium fertilizer rate and timing guide, and so mainly in the corn area. And so with that, I will turn it over to Jason to kick off the program here today.
All right, well, thank you everyone for coming today. We're going to start out with a little bit of a quick poll here. I have several presentations that we can kind of give today, but I kind of want to do a choose your own adventure theme with everybody. So I think Matt threw up the first poll here. If you want to go through and just answer those, it'll help me know where you want me to focus today and how much time on which of these topics. So I believe that's up. And if you just want to click on a couple options, then we'll know what you guys want to hear most about today. All right, we're getting some answers in. Just for a quick aside, while we're waiting for some people to answer some of these questions, some of these videos that we're working on today that I'll show you on some of the nitrogen rate updates will be up on the YouTube site as well. So you can check those out later, get some reminders from this presentation as well as far as what we're finding out regarding corn nitrogen fertilizer rates. And I'll show you that towards the end of the presentation. The second question is just more of a curious. I was talking to some students and talking about some yield differences, and I was curious at what point you all want to see a management practice or fertility practice change your yield before you're going to be really interested in implementing it. And it looks like 10 to 20 bushels seems to be our winner at the moment there. So it's looking like accuracy of corn nitrogen recommendations is where we'll spend most of our time, and then we'll hit interseed and cover crops just a little bit towards the end, I believe. All right. Okay, well, thank you for that. Let's see if I can, let's see if that shares results. All right, I think you can actually see those now. So yeah, we'll spend more time on accuracy of nitrogen recommendations and then the phosphorus, potassium, sulfur update. And looks like we want to see at least a 10 bushel per acre yield difference before adopting some management practices. Right. So I will go ahead and share my screen here. Okay. All right, so we wanted to go to active nitrogen recommendations, so we'll click right here and go there. Oops. Okay, so just kind of a little bit of background as far as this goes is that in the last 3 years, we've done about 21 nitrogen rate sites that are in this presentation today. So in 2018, we had 7 sites, 2019, 10, 2020, we had some restrictions on research, so it was only 4. We have several more that'll get into this database here in the near future, but this is what this presentation is based on. We have conventional and no-till sites, and mostly soybean was the previous crop with wheat with some. So just a little bit of background information on those as well. These are the locations of the sites. We do have a bunch more over in this area, and that will get into the database this coming winter and spring to update everything. So what we do at these research sites, just for some background information, is we'll go in there and we'll put nitrogen fertilizer rates ranging from about 0 to 200 pounds per acre. And here we can see we have our corn yield on our y-axis and our nitrogen fertilizer rate on our x-axis. And what we want to do is we want to see how yield changes as we get that nitrogen fertilizer rate. And as we can see here, it's pretty typical. This is at Salem, South Dakota research sites this past summer. We can see we're increasing in yield. And then somewhere between here and here, these two rates of 80 and 120 pounds of nitrogen per acre, we seem to plateau. We kind of go flat. We don't know exactly, we just know which one it is. And then from there, we usually do some sort of math to kind of estimate what that point would be. And depending on who you are and what your thoughts are, there's this linear type of model, which would tell us our optimal rate is about 90 pounds. This other model is called the quadratic one, and it would tell us it's about 120 pounds of nitrogen per acre that you need. The real answer is probably somewhere here in the middle. But it's somewhere there, and that's kind of what the math tells us. So there we have about 31 pounds of nitrogen per acre we need. We both end up yielding the same amount with either way we do it. And if we do the math, supposedly if you go either route, you're going to be making money. If you add 31 pounds of N, you're still going to get about 9 more bushels an acre, just out plus 21.67 per acre. Just on that. So this is what we did at each site. And then what we're going to focus on are these points here where we plateaued and see how accurate our current system is with them. So if we look at the 21 site years, we had quite a range of nitrogen rates that optimize yield, and we can see that here. We had these first 7 sites here that didn't respond to nitrogen at all. That might be just because of good management practices. Some fields had drought problems, other fields had too much water in these different years. You can see a lot of them were in 2018 and 2019, which we had a good amount of precipitation there. But the other thing that's kind of interesting with this is just because we took anywhere from 0 to 133 pounds of nitrogen per acre doesn't necessarily mean it affected yield. Because if we look at our yield at each of these sites, we see we have a good range of yields. So our yield did not necessarily relate to how much nitrogen was required to optimize that yield. So if we look at our different nitrogen recommendation options, we can see that we have 2 main ones. We have our current one that we have a yield goal system. There's also what's called the maximum return to nitrogen. The one we're going to focus on today is our current yield goal system. And in the future, we'll compare that to this maximum return to nitrogen that Iowa and Minnesota and some of the other states use. But if we blow this up and we look here at our nitrogen fertilizer equation, we see this right here. We see that our nitrogen recommendation is our yield goal times our 1.2 minus our soil test nitrogen, minus our legume credit, and then we have a no-till debit if you're in recent no-till. So if we take a look at that equation and we throw up a quick example here, if you say your yield goal is 144 bushels per acre, we'd multiply that by 1.2 for the amount of nitrogen per bushel of corn, subtract our soil test value, and just use an example of the Salem, South Dakota site of 58 pounds of nitrogen per acre was in the top 2 feet. And then it was following soybeans, so we did 40-pound legume credit. And then if we were to say it was recently no-till, we'd add 30 pounds of nitrogen per acre. So once we do that, we'd say the recommendation for this site was 105 pounds of nitrogen per acre. And we say our urea source, our source of nitrogen is urea, 46% N, so we divide that by that. So we're going to apply about 228 pounds of urea per acre. So that's an example of what our recommendation would be in this field. So the question is, everyone wants to know how accurate is our system and do we need to change anything? So if we look at these 21 sites here, we're going to kind of go through that equation quickly for each of them. We take our yield goal for each of those sites, we multiply it by 1.2, and this is the amount of total soil test nitrogen we need in each of those fields. So from here, we're going to subtract our soil nitrogen, and these are the levels of fertilizer we'd recommend. For those fields that have a legume before it, we then subtract that amount of legumes. So this is our current recommendation. And some of these fields we saw earlier, about 8 of them have no-till. So we'd add 30 pounds of N to them. And you can see a few of those sites changed here. So this right here is our current, what we would recommend for each of these sites. So now what we want to do is that's our recommendation. What did we actually need? So let's take a look again. This is a recommendation, and now this blue bar is going to be what we actually needed at each of these sites. So what we want is we want that blue bar to be as close to that red bar as possible, and that means our recommendation is as accurate as we can get. So let's see what we got. So here we can see that some of these are pretty close. That's 10 pounds off here, where we actually needed a little bit more here, about 50 pounds more in there. And we actually needed quite a bit less in a couple of these sites, but some of them are pretty accurate. So we're going to look at this a little bit differently. So here, instead of looking at the absolute values, is I took that nitrogen recommendation rate and I subtracted it from that optimal nitrogen rate. So now this is the difference. So this 0 line is where we want to see things. So if we have that line above 0, that means we overestimated that site. If we have it below 0, we underestimated at that site. So you can see some of them, we want them close to 0. We have some of them that are fairly close, within 10, 30 pounds of nitrogen per acre is actually a pretty good estimation. But we have some of these that are pretty high overestimations still with this current recommendation system. And these ones with X's on them here, these are sites that didn't respond to nitrogen, so which is not what we would have concluded, which is why a lot of them are quite a bit higher in nitrogen overestimation than the others. So we have to remember that, and I'll show that a little bit later here. So on average, we're about 68 pounds of nitrogen per acre over. If you get rid of those 7 sites, we're only about 38 pounds of nitrogen per acre on overestimating, which is pretty good as far as an overall average across 3 years. But the ultimate question is always is, can we improve? Can we do better? And can we be more consistent so we don't have such high extremes? So if we look at this yield goal equation to see where we can improve, a lot of the area of curiosity has been around this 1.2 coefficient. Does it need to change? So if we take this 1.2 coefficient and look at where it comes from, we can kind of do some calculations to see how currently accurate it is. So from here, we can see that to calculate this, we'll take our soil test nitrogen value and our fertilizer nitrogen rate that was required to optimize yield, and we'll add those together. So in this example, it's 240 pounds of nitrogen per acre. And then from there, we're going to divide that by our bushels per acre. So here, 200 bushels per acre. And then once we do that, we do the math, we required 1.2 pounds of nitrogen per bushel of corn. And that's where that 1.2 comes from. So in long-term average, that's what it was. So what is it currently? Has it changed with management practices? Has it changed with hybrids and things like that over the years? So if we take a look at this and we calculate that same thing for each of those sites, we take our soil test nitrogen values that we had from 0 to 24 inches, and then we add our optimal fertilizer nitrogen rates. And then we're going to take that number and divide it by this green bar, which is our optimal yield. So once we do that, and we also have these sites here that we're going to keep an eye on. So once we do that, we're going to get a number between about 0 and 1.4. So this line here, that's our golden line, that's our current 1.2 value. So we want to see how close each of these 21 site years are to that 1.2 value. So you can see overall, we have some of these sites that are right on at that 1.2 value, some that are pretty close. We have some that are quite lower. If we take the average of all of these sites, that bar actually moves down to closer to 0.7 pounds. But if we get rid of these 7 sites here, we move up a little bit to around 0.9. So what we're going to do is we see that there's on average, we're a little different than 1.2. So then the question becomes, if we change that 1.2 value, how accurate are our nitrogen fertilizer recommendations at that point? So from here, we're going to look at the same graph where we have the difference. The sites with X's are those sites that didn't respond to nitrogen. So we want to see how close, again, these sites are to 0. 0 means we are perfectly accurate as far as our estimations and our actual required. So first of all, we're going to use the 1.2 difference that we saw already. And we can see that here. And now this blue bar is going to be our 1.0 difference. So we're going to change that coefficient from 1.2 to 1.0, and we're going to see if that helps each of these lines get closer to 0. So from there, we can see that a lot of the sites got closer to that 0 mark, which is what we want to see. Now we're going to jump down to 0.8. So if we change it to 0.8, we see that same thing. A lot of those sites are tending to get a little bit closer to 0. However, we also see kind of something interesting. These sites like right here that tend to overestimate, they are getting closer to 0. And this site here is almost perfect with that between that 1 and 0.8. However, these sites that tend to underestimate, like right here and here and these ones over here, the lower the coefficient we get, the more we're underestimating our nitrogen fertilizer needs. So what we're going to do is we're going to kind of group these different sites. We're going to look at the sites separately. These ones that tend to overestimate the most, the sites here that tend to underestimate the most, and then we're going to look at the 50% in the middle. So first of all, those sites right here that tend to overestimate. So first of all, that 1.2 difference. So overall on those sites that tend to overestimate, we're overestimating by about 157 pounds of nitrogen per acre. Now, if we move that coefficient down to 1 and then 0.8, we see that sites that tend to overestimate a lot, we need a lower coefficient. Now we're going to move over to the ones that underestimate. We're going to see the opposite trend. As we go from 1.2 to 1 to 0.8, we tend to increase the amount that we underestimate. Now this next one is where most of our sites are going to be in most years, is in this middle 50%. So if we look at these, we see that we go from a 64 pounds of nitrogen per acre overestimation to 28, down to actually underestimating by 8 pounds of nitrogen per acre. So overall, moving that 1.2 coefficient from 1.2 to 1 and maybe somewhere between 1 and 0.8, or if we take a little risk management around 1, is going to overall most of the time with the data that we have now is going to lead to a more accurate nitrogen recommendation. If we look at this data just a little bit overall, a little bit different way, if we take it all together, we can see this here. Inside the box, we have about 50% of our data, and we have about 25% above, 25% below. And you can see overall, as we move from 1.2 to 1, we get closer to this red line of 0, which is where we want to get. Now, of course, we have to get together all of this other data that we want to look at before we make any final decisions, but it's looking like that coefficient could definitely decrease from 1.2 to at least 1 to help improve our accuracy. And also a lot of people are curious, these ones tend to need that higher one, these ones tending the lower one, these ones tending the higher one. That's also what we want to look at in the future, is trying to better understand which ones are we underestimating and which ones are overestimating. Is it a issue of soil test nitrogen, soil health, organic matter, something else that we can measure? So maybe we vary that coefficient at 1.2 in some areas and 1 in others. And that's something we still have forthcoming in the future. Let's see. So that's kind of a quick update there. Have a little bit of time, so we're going to jump to our interseeding trial before we jump to the end here. So this will be our next little adventure we're going to go on, and I'll go through this pretty quick. And you can always feel free to email me or talk to me about some other questions as well. But here, the study is set up as a corn soybean rotation. So I have corn and soybean present each year, and it just switches back and forth each year. And then within each of these, we have 3 cover crop treatments. We have a no cover, we have a single grass species, and we have a grass broadleaf mix. And then for the corn, what we're doing within there is we have 6 different nitrogen rates for each of these cover crop treatments. So we want to see if our nitrogen requirement changes based on our interseeding of cover crops. And that kind of, the graph ends up looking a little bit like this right here. We have 3 different lines on it, and we kind of want to compare at what point these 3 lines are plateauing. And we'll look a little bit more at the site in just a second. So we're going to jump to just to our yield stuff. If you want to see some pictures of the interseeded cover crop, we can do that later. So if we look at our Brookings 2019 site and we look at our cover crop, or no cover crop, we have yields that looked about like this in our Brookings site. Our grass cover crop, things are pretty close, pretty on top of each other at each of those rates. And then our grass broadleaf. So we see at 0, we're pretty close to each other. At the 75-pound rate, we see grass and no cover are really close to each other. And then the grass broadleaf was a little bit lower yielding, but once we hit up to about 150 pounds of N, we seem to be right there with each other. So if we do the math of the lines for each of these, we see they're very similar. We do see that the grass broadleaf was a little bit lower yielding here and took a little bit more nitrogen to reach our optimal yield. So that's one trend we saw in this site in 2019. So you can see the differences of where these totally plateau. This one, if you look about right here, as far as yield, it's about 30 bushels per acre difference, 20 to 30 bushels per acre difference between our grass and our no cover crop. Once we give it a little more N, it yielded the same pretty much, but it did require a little bit more to get there. It's probably about 100 pounds per acre. You probably couldn't tell much difference statistically. So if we look in Beresford down the southeast part of the state in 2020, this is what we saw there for our no cover. Our grass, a little bit more variation in yields, and again, our grass broadleaf, so pretty close to each other. Again, overall, we see here as we optimize those N rates, no real difference between grass and no cover. And again, the trend kind of seemed to be this, that grass broadleaf took a little bit more N to get to where the grass and no cover were. Not exactly sure why that would be. I would have guessed the other way around. But we're looking into some more of the soil tests this winter to see if it can help us better explain some of that. The reason this is over here is because this never totally flattened out. It's just what we call linear. But overall, as you look at the differences right in here, again, we're around that 30 bushels per acre difference between the grass broadleaf and the no cover and grass treatments here. And this is Beresford 2019. Beresford 2019 had some yield issues with some wind damage, but we can see here, if we look at the different cover crops, as they come up between no cover crop grass and grass broadleaf, very little, if any, difference in these 3. It actually didn't really even require nitrogen at this site. But that was more due to wind damage than anything. And I'll show you a picture in just a second. So this is our Beresford site, and what we tended to see is things like this. And what we're missing here, we look right here, is we're missing these stalks. And that's because we had wind damage at each of these. And you can see here, the stalk that should have been there is now down here, which is not what we want. But kind of the interesting trend here, if we look at stem breaks on this y-axis against nitrogen rate. So for no cover crop, this is what we see, an increasing amount of stalk breaks as we increase in nitrogen. For grass, similar. Grass broadleaf, similar trend. So this is almost like a nitrogen response curve. We have increasing stem breaks with increasing nitrogen rates. And that's likely why the 0 N rates in 2019 yielded the same as these higher rates, as we had higher stalk breakage in the higher rates of nitrogen. Yeah. All right. So that is it for my stuff. I don't know if we want to hit questions here, if we want to just jump to Anthony, if you want to go through your nitrogen stuff next, and then we can go from there probably.
Jason, I've been answering some questions in the chat for you. You may want to go back through that and review that a little bit. I knew some of those answers and just threw that in there to kind of keep up with that. So yeah, I can. This is a study that Chris Graham and Jose Gonzalez, and they included me as well. It's the question, the longer we're in a no-till management system, what happens to the nitrogen rate recommendation? And Jason covered that in his presentation. He had some no-till sites there, but here we're specifically separating that out and looking to see those differences. Now, research like this is very difficult because to get a long-term no-till plot, we would have had to set these plots out 20, 25, even 30 years ago and have them in a replicated, randomized setup, and that's almost impossible. I know Dwayne Beck at the Dakota Lakes Research Farm has long-term no-till, and Peter Sexton at the Southeast Farm does as well. And our own Sarah Bowder did her master's work on looking at those nitrogen rate comparisons in the long-term no-till to conventional till, but we didn't have any short-term no-till there at that site. So this, excuse me, this is a across-the-fence approach where we were able to find two fields, one that had been in long-term no-till for a long time and the other in short-term no-till, and did the same research protocols as what Jason showed you in his presentation. The nitrogen rates were the same as far as the plot design and everything. And so as Chris has put up here, the agronomic optimum N rate is the total amount of N soil plus fertilizer, which the yield is maximized. And so it's not necessarily the economic rate, the economic optimum nitrogen rate. So we can see here that these curves, especially for the short-term no-till, has that linear uptrend at those lower rates of nitrogen, meaning that it's more starved for nitrogen in there, and that probably the organic nitrogen sources are not built up as well as the long-term no-till. And so we can see that they're depicted in that graph under the long-term no-till. That curve is more flat across, and so it's not responding to nitrogen as well as the short-term no-till. And again, these two sites were within a short distance of each other, and the nitrogen rates were calculated there at 197 pounds for the short term and 136 for the long term. Jason, you can go to the next slide. And Chris has calculated the production efficiency here, and because the long-term no-till took less nitrogen, it has a higher production efficiency. We're getting 5 to 6 bushels per pound of N there in the long-term no-till at the beginning of that curve, when we're only getting about 3 pounds or 3 bushels per pound of N for the short-term no-till. He's calculated that out here at the bottom of the slide. Short-term no-till 2.2 bushels per pound, we're less than 110 pounds per acre. And then the long-term no-till, we're getting 3.9 bushels per pound of N, where rates less than 110 pounds per acre. We can go to the next slide. I want to shift gears just a little bit here. This is my part of the presentation. A lot of questions we get from producers is, I can't switch to a conservation tillage system or a no-till system because I can't deal with my fertility program. And there's a lot of data, and the database is still growing on comparing broadcast applications of nutrients to banded or subsurface applications or tilled-in applications. This is a study at the Northeast Farm that was started in 1996. It was tilled up until 2004 and then converted to a no-till plot. And each year, 40 pounds of phosphorus, 50 pounds of potassium, and 5 pounds of zinc are applied to the same plot. And then if you see the treatment treatments here, we leave off one nutrient in the presence of the others. The others get applied. So this would be our no N, our no P, no K, and our no zinc. And you can see the effect on soil tests, of course, where we haven't put on any phosphorus. Since 1996, we're at 3. It's probably not going to go any lower than that because we won't have a 0. That's coming from the native phosphorus in the minerals. And so that's just going to stay there, steady state. Our K is somewhat reduced at 110. And again, we have a lot of minerals that are bearing potassium in our soils, and we'll keep that up there, but we don't know, that could drop even more. Zinc in our checks is still at 1.1 part per million. So we're above our sufficiency level of 1 part per million. So we wouldn't recommend any zinc be applied at this site, but it's interesting to see how we've built up our zinc tests. So if we quickly look at the grain yields here, we can see a huge response to nitrogen, almost 75 bushels there, response to nitrogen, 140 was applied to this corn this year, and a huge response to phosphorus as well. Okay, so this phosphorus has been applied to the surface since 2004. So I want to go to my last slide. This year I took some incremental soil samples by 1-inch depths. You can see those depths on the left-hand side of this table. And I was interested in the phosphorus and potassium and zinc stratification, but mainly the phosphorus stratification. You can see here we have high stratification in the plot that received phosphorus under the Olsen P column here. This plot received phosphorus. We're at 28 ppm in the 1-inch depth, and in the 1 to 2 we're at 10 and 9, and you see how it goes down as we go deeper, by 1-inch increments. If we compare that to the control that hasn't received any phosphorus since 1996, we're much higher. But I would also like to point out that at each one of these depths, we are higher than the control. You would think that if phosphorus doesn't move, they should be the same as that control, but they're slightly higher. And even in this 1 to 2-inch depth, we've seen some movement down. So what is happening there? Phosphorus gets absorbed to the soil by ligand exchange sites, and quite possibly maybe those sites are full, and so then that phosphorus has to move down to where there's more ligand exchange sites available. So you can see we have stratification here of phosphorus, definitely, but we got a huge response to phosphorus. You seen that in the previous slide by that big yield response. So with that, that's what I wanted to cover today. Jason can take back over and continue on.
All right, so I think I'll take a second here and we'll answer some of these questions from some of the people that popped up in chat. Not sure if there's one in Q&A. Oh, someone asked, how many years is short-term and long-term no-till? Do you have that, Anthony?
That's a good question. The 30-pound debit that Jason referred to came from a number of studies that we did in the late 90s and early 2000s. Those no-till plots were ranged from 6 to 8 years. So at that time, that was long-term no-till because we didn't have any longer no-till to do our work on. Sarah's plots for her nitrogen study that she did, I believe, were 24 years of no-till. So somewhere between the 6 and 8 and the 25 is the break, and we don't know. But certainly, I think if you there's been a huge emphasis on soil health. If you try to ramp up your soil health with rotation and cover crops and no-till and maybe livestock grazing as well, I think that reduces the number of years before you get to maybe a more mature no-till situation. So while I can't answer that, specifically, I gave you some thoughts and ideas to think about.
Anthony, if I jump in there really quick, I'm not sure if I was read or hearing that question correctly, but within the study that we had between the two presented with the short term and the long term.
Sure. The short-term no-till was a field where it was just transitioning. It had been really good conservation tillage for a number of years, kind of only tilled every other year in preparation for the corn. And then the producer decided to go no-till. So he was in his third year of true no-till at that short-term no-till site. The long-term no-till was about 27 years.
All right, thank you. Hopefully that answers some of that question. So another project we are working on is a lot of these soil health measurements are being promoted at this time, and we're trying to see if any of those can help us determine at what point we can either take away that 30 pound per acre increase in nitrogen that's needed, and also when we need to add it. So it's another project that's working on with several different researchers here at the university, and hopefully in the near future, we'll have some better answers as far as being able to tell when to get rid of that credit in that regards. So some of the other questions talked about how would you explain the little response to nitrogen in the wet year of 2019? Because a lot of times we think if it's really wet, we're losing nitrogen through leaching and denitrification. And a lot of times that really depends on your soil. If you have a sandy or coarse textured soil, if we have good rainfall, you're most likely going to lose that nitrogen. But a lot of our loam, clay loam soils, our soils can hold on to that water a lot better. So we're not as likely to see as much leaching and denitrification losses in those years. And what that moisture year did in 2018 and 2019 is it really kept that organic matter being decomposed, being turned from organic nitrogen to inorganic nitrogen, where the plant can then use it, which reduces that need for nitrogen really well. Whereas if we have a dry year, and the plant relies more on probably fertilizer and to get that yield. When we have wet years, the microbes can do more work longer into the season and provide that end. So that's likely why even in wet years, we're actually seeing lower end needs. And if we get really wet, then we're going to reduce yield based on the water being too saturated or the soil being too saturated. Another question came.
Jason, can I add to that a little bit? If it's okay. I really expected that year to be a really responsive site. And so I was surprised as well. I mean, I tried to answer that question a little bit as well in the chat, but, even in the same field, sometimes we had two wet areas that Jason just talked about where we probably lost a lot of the nitrogen. But in the same field, I think we had, especially in the hillier landscapes, we probably had soils that were still able to crank out a considerable amount of nitrogen. So depending upon where you're at in the soil type, even within the same field, we could have had some big differences.
Yeah.
Jason, your last chat went to panelists, just an FYI.
Oh, did it? Thanks. So the cover crop was interseeded into the corn near the V5 corn stage. That's where that interseeding project was. And that project is in its second year. So we've applied cover crops at V5, corn and soybean at both years. So we're going to see over accumulation of years how that nitrogen rate continues to change. So this is an ongoing project. Let's see. So have you seen another question? Have you seen any benefits of split applying nitrogen? I don't have that presentation up today. Peter Kovacs and I here at the university have been working on split applications. I think Anthony's done a bunch as well. As we've on split applications, we've seen some benefits in some parts of the state. And I don't have that information, but we do have a research report that I'm hoping to get up on the extension website soon. I don't know if Anthony, if you have a general idea of some of the stuff that you've seen that you want to answer that question a little better with.
Thank you, Jason. Yeah. We do get responses to split application. I have to say that, but they've been minimal. So if you're in a split application program for a number of years, you're investing that time and that effort in doing that, the probability of getting a response to that split is lower than what you'd want, I think, from what I've seen. But it does happen. I've got a lot of delayed application, nitrogen application work that I've summarized in. And I'm glad that Jason asked the question at the beginning, how many bushels do you need? So, you know, if you get 25% of the years, or let's say 30% of the years, you get a response and it's 10 bushels, that's 30 bushels, but you really need to divide by 10 because you're going to do that over a 10-year period. So then you really reduce that advantage. So those economics are quite interesting to think about.
A couple of your questions for your stratification study are, can I see the potassium and zinc stratification when K and when N and when zinc is not applied?
Oh, say that again, please.
Can I see the potassium and zinc stratification when potassium and when zinc is not applied?
Okay, I did not sample those plots. That is something I need to do. I just sampled these because, as I mentioned, I was mostly interested in the phosphorus stratification, and we tested everything else because, well, we could, but I hope to make a larger project out of this and do that work. So thank you for your interest.
Did you see any pH changes with stratification tests?
Boy, yes. And now you've tasked my memory to recall all those numbers. It's not coming to me. I'm sorry. If you would like to see this, some more of this data, please get in contact with me, and I will certainly answer your question at a later time.
All right. Okay, so I think we've hit most of those, and to give us enough time to kind of hit this other part of this study, we're going to jump to this potassium, phosphorus, and sulfur update. And then I'm going to close out the chat and the questions so I can see everything, and then we'll answer stuff at the end. I'll leave enough time. So there's kind of two studies built in here. One is looking at potassium rates. The other one is looking at just with and without phosphorus, potassium, and sulfur to try and identify how accurate our current system is and what areas might need some more attention to. So in this one, if we kind of look at our crop fertilizer recommendations, they're based off of graphs that look like this. We have our relative yield on our y-axis, and we have that in relation to our soil test level categories going from 0 up to however high they are. And what we're looking at is where does that yield go up, and at what point do we no longer, what soil test levels do we no longer see changes? And what a lot of questions we have is, does this critical level need to change? So for potassium, this is 160 parts per million. For phosphorus, I think it's 16. So do those need to change? So that's kind of what this study was looking at. Are those values. So what we did is we took a lot of farmers' field and we just had what we called these stamps out in their field. So we had a control where we didn't have phosphorus, potassium, and sulfur. We added potassium, we added phosphorus, we added sulfur, and we had two other treatments in some fields where we added P and K and then all three nutrients. And what we wanted to see is we wanted to compare these treatments where we added fertilizer to where we didn't add fertilizer to see how much of a yield change we got based on our soil test values. So what we did is this is an example of a field that we did in the eastern part of the state. And what we did is we took these four different areas, kind of a low sloped area, hilltop, mid slope, and up on top. So four different areas of a field. And each of these, we put this stamp there. So the farmer didn't apply any nutrients. We took that area and we applied all the nutrients and then did tissue uptake of nutrients as well as yield at the end of the season. And if you look here from 2019 to 2020, these are the sites where we've been able to accomplish this research. And we were hoping to have more of this last year, but COVID hit us. So if you're interested in being part of some of these studies, feel free to shoot me an email and we can do some work on your farm as well. So we're going to go quickly through some of the individual nutrients until we don't have time. But the phosphorus one is where we hit the most. I think we saw the most interesting responses out of this one. But what these graphs are going to look like, just to kind of go through them, is we have our tissue response here on the y-axis. So at 1, and that means that that we didn't see any differences. So the control is 1. So if we went above that line, that means we increased yield. If we were below that line, that means we decreased yield. So for example, if our control is 1 and then another treatment is 1.5, that means we increased our yield by 1.5. So if this is 100 bushels per acre, this is 150 bushels per acre. This is 100, this is 50 bushels per acre. And then what we did from there is this line right here represents our critical value. So with phosphorus, it's 16 parts per million. So if our test is below that line, we're saying it's going to be responsive, most likely going to be responsive to fertilizer. If it's above that line, we're saying it's not going to be responsive to fertilizer application. And what we want to see, or typically would see, is a curve that looks something like this. Sites that were low were very responsive to fertilization, and as we increased, we decreased our responsiveness, how much we're increasing yield, till we kind of hit somewhere flat. And we want to see if this point where we hit flat is similar to that 16 or if it's changed some. So if we're up here, we're responsive, we increased yield, that's what we want. If we're over here in this area of the graph, we would say we are non-responsive, but when we added fertilizer, we actually increased yield. So that's not necessarily what we want to see. And if we're on the line, that means that we are non-responsive, we maintain yield. So that's what we want to see. And if we're below the line in this segment of the graph, we were non-responsive, but when we added fertilizer, we decreased yield. So we kind of want to see that because sometimes we think if we add fertilizer, it's always going to increase our yield, but there is a potential that it will decrease. And we'll see that in just a second. And if we're in this part of the graph, what we're saying is we think it should be responsive, however, it actually decreased yield. So it's not what we want to see, is we want to minimize the amount that's in those. We want to minimize the amount of points that are in this area and increase the amount that's right here and on this line. So then if we look at the actual one of our sites here for our phosphorus uptake, this is V6 plant uptake, and our 1 line is our control. That's right here, and we have our 16 part per million. So then if we look at the points here, this is kind of the results that we've gotten at all of those research sites. So it's kind of scattered, but we can kind of generally see as a trend that kind of goes flat right there. And if we do the math, we see 52% of our sites were within that area, which is what we want to see. There are 12% that were still below the line. So we're saying that we should see a response, and we added fertilizer, but we actually decreased yield. So we're kind of curious of why some of these sites ended up here. If we look at them, some of them are still pretty close to the 1 line. And if we look over here, we still have 30% of the sites where we said it's above that 16 parts per million, but we still increased yield when we added fertilizer. And then the bottom one was at 6%. So these are the sites that we said don't apply fertilizer, and they did, and we saw a decrease in yield. So the kind of curiosity is, if we look at this line, we almost maybe see, instead of this line, we almost see something that looks almost about like this, and then goes flat. So my curiosity was, with this data, 58% of the time, the amount of data that's in here and here is correct, but what happens if we move that line a little bit, say 20 parts per million Bray phosphorus, what happens then? So we move that 52 to 70%, that 12 to 14%, which is what we want to minimize, but we actually reduce the amount that we're under fertilizing from 30 to 12, and that decreases. So this almost shows us that maybe our phosphorus recommendations need to be looked at a little more. One thing we have to understand as well is this is still preliminary data. A lot of these responses that we saw are right here, and they're not too far from our 1 line. So there is some area there that we could maybe look at. But this is phosphorus uptake at V6. Our early season stuff tends to be more responsive to fertilizer. So if we switch this over here, and now we're going to look at phosphorus yield response. Oops. So if we look at that here, we don't see as much, and we hope we put that line there. It seems to be there, but not quite as well as what we'd like to see. It's a little bit flatter. Might actually be somewhere down here. But we do still see this group right here that tends to respond. So if we leave it at that 16 part per million, we have 52% of our sites that are responding, 15% that decreased yield when we added fertilizer. There are 27% of the sites that we said wouldn't respond, but still did. And then we had a minimal sites that decreased yield. So if we kind of look at this, we had 58% of the time again that we were correct, similar to our P uptake. If we do look at that, we move that 16 to 20, we change a little bit, we go up to 71, and we decrease if we just focus on these two up here. We increase that some by moving this line. So we'd say, yes, you need to fertilize these sites right here, and we'd see a response. So that did help in that regard. So this kind of shows us that maybe in some areas of the state, we need to look more about our corn phosphorus rate guidelines. It doesn't tell us how much nitrogen we should apply. It just tells us that we responded. And the amount that we applied here was 100 pounds of P, 100 pounds of K, and 25 pounds of sulfur when we add fertilizer. So we just wanted to see how much, if we'd see a really increase in yield. The next step to some of these would be doing some of these rate response trials where we see at these difference, you know, if we were at a field between 60 and 20 parts per million, how much phosphorus would we need to add in order to get some of these yields? So, some of the other big questions we've seen is what about potassium? So potassium, we're looking at the same type of curves or same type of information here. We can see it, this is what we saw. If we look at our 160 part per million break and our 1, so we're kind of, we want to increase the amount of data that's in this segment, decrease what's in here, and we want to minimize what's down here. So here we can kind of put this curve on here, and it looks okay. It's not the greatest data. We need to increase the amount of data that's in this site, and we're going to continue this research this next summer, which will help us in that regard as well. So we can see the amount. We have 31% here, 10% that we're losing yield. So sometimes we can still lose yield when we add potassium. 35% that's saying that we should apply more. So then a lot of the question is some of the data in both Minnesota and North Dakota have said we need to actually move this line to 200 parts per million, depending on the soil type. So if we do that in this data set, we see a little bit of change. But what we actually see is we actually see the amount increase in yield reduction when we add potassium fertilizer. So we don't want to see this number increase. We want to see this one increase and this one decrease, which they both did some, but not a lot. And these sites right here, we need to spend a little bit more time on, and I'm hoping this next summer to get more farmers in the eastern part of the state, specifically the Northeast, in those areas where some of these times they're thinking they're getting more responsive out of these higher potassium from 160 to 200 part per million potassium soil test levels. And so we're hoping to get some more farmers to help us with getting some more data here just so we can better validate if this point needs to move. But based on this current one, we don't see a whole lot. And this is V6 plant uptake. If we look at just yield, we see a pretty good scattering, 160 part per million, that one line. And then we see here that that line doesn't really look great. This is just me imposing a line. It's not the actual line. But we can see there's here, and if we change that line up to 200 parts per million, we see a little bit of an increase there, also an increase in yield reduction, some decrease there and some decrease there. So the phosphorus looks like we need to take a little in-depth look. The potassium, not as much, but I want to try some more sites in some of the eastern parts of the state where we potentially have some of these. And along with this test, and I don't have the data evaluated yet, we also looked at clay mineralogy, similar to what North Dakota did. And we're going to be incorporating that into this data to see if some of these points that are right here that are still responding potassium at these higher levels, if those have certain clay types compared to these sites over here that don't respond to it. Let's see. And so this is sulfur, and I just have a one-to-one line with sulfur because I wasn't able to get all the soil measurements that we need for this. But you can just see here that for our sulfur trials, the ones that we saw, this is just soil test sulfur 0 to 6 inches. I'm still working on getting the 6 to 24 inch that we need to fully follow our recommendations to evaluate them. But we can see we're still getting, in a lot of parts of these states, we're still getting a good response. This is V6 plant uptake. If we look at yield, it's a lot different. 54% of the time, 46% of the time. And this is why in our sulfur recommendations, we don't rely just on the sulfur soil test, but it also incorporates soil type, because we see sulfur response more in coarse textured soils and also based on tillage. But that'll be forthcoming. So it's just some preliminary data that we see as well. With that, let's see. So with that, I think before, let's see, oops. I think we probably have questions.
Yes, you do, Jason. There's a couple in the question and answer, and I think you should answer those.
All right, how many of the P sites were no-till? The no-till sites, 6, 7. It was about half and half in 2019, and they were 5 of the 6 sites were no-till in 2020. So there's a good majority of no-till sites in these phosphorus sites. I don't have which ones are which at the moment, but it's about half and half, I bet, over the 2 years. As far as that goes, and another question is, do you have any ideas to explain the yield decreases with added phosphorus? That one I'm still working on as far as potentially explaining those, as well as the potassium. Some of the potassium ideas, and they've seen similar things in both Minnesota and North Dakota with addition of potassium or phosphorus decreasing yield. And it could be something to do with salts or other things, but we're not sure on that one. I wish I had a better answer for that, but that's one thing we'd like to better understand. As far as that goes, let's see.
There's a question in the chat as well, Jason.
In the chat, the P and K was broadcast applied in all of these sites. We're working on small areas within each of those sites, so we had to go in and do it by hand to get the different soil type areas, so it's all broadcast on the surface. The points in the bottom left corner, if I can get back to them. These are sites that we'd say we need fertilizer application because they're below that soil test level, but we saw a decrease in yield when we added it. So these ones right here, and they're not much. This is at 1 and this is 0.8, so a decrease of 20%. So some of these did get a decent decrease in yield. And we're not sure exactly why. I talked to my colleague in Minnesota, and they're still trying to understand why their thoughts are maybe something to do with the EC levels or salts and things like that. How long does it take elemental sulfur to become available? I believe it's a few months. Anthony, you've worked with more with sulfur.
Yeah, that's a very good question. The elemental sulfur transformation in the soil is biologically mediated. And if you have not applied elemental sulfur, the level of that biology is restricted. And so it takes some time to build those up. While I can't answer the question exactly, because it depends on soil type and environment, but you would think that it would be on the order of many months over the growing season. But again, I don't know exactly. Compare that to the ammonium sulfate forms, which are readily plant available. They don't need to go through that biological process. We have not put out studies to measure that rate of change, but it's always something that's on our list. So very good question.
I'm not seeing any more questions. Here's my contact information. This is my email. Feel free to give me an email. You can also find my phone number online and shoot me an email or give me a call anytime. These are our social media outlets. If you want to get up to date, I usually will send out updates when I post an update on our research trials. If you want to know a little bit more about some of these information that we have here, I currently am working on putting some of these up. If you go to the YouTube site, SD State Soil Fertility, you can find some of these. They'll be up later today. We have things about estimating yield goal, calculating crop stems, the accuracy of our current yield goal system. If you're curious about the accuracy of that +30 no-till debit, I have some information on that that'll be up in the next 2 hours is my goal. And so this is somewhere that you can go to find some more of these presentations and also get some reviews. There'll be some short videos up shortly in that regard, but these are some of them that you can follow, and then I'll let you know when they go to YouTube or I post something on the extension website. Let's see, I don't see any other questions. If you have any questions, feel free to put them in chat or the Q&A.
Okay, while we're waiting for that, Jason, Matt, why don't we put up our poll? And I put in the chat our site to go to have some more discussion afterwards into a Zoom. But before we get to there, we need to put up our, when the poll ends here, we'll put up our codes for CCA credits. We'll give a few more seconds for anybody to cover there.